First question of the homework 2 uh, is 2 kg piston supported on the helical spring vibrates freely with a natural frequency of 120 cpm. When the oscillation within an oil-filled cylinder, the frequency of the free vibration is reduced to 120 cpm. And determine the damping constant C. So in this problem, the question is to tell how liquid medium damps out oscillation of the spring mass system, and how to calculate the damping constant from the observed reduction in the frequency. So to solve this problem, here we have to determine the damping constant given that the piston mass of 2 kg and this is the undamped frequency omega n is 125 cpm, and the damped natural frequency is 120 cpm. So now we will consider the two cases. One, when the piston is in air and when the piston is in oil. That is when the damping is present and when the damping is negligible. So when the damping is negligible, equation of motion for the piston on the spring is mx double dot plus kx is equal to 0. So the damped natural frequency is undamped natural frequency is omega n under root of k by m. So the oscillation for the x of t is equal to a sine omega n t plus phi. But when the damping is present in the oil, so the equation of motion becomes mx double dot plus cx plus kx is equal to 0. So the undamped natural frequency, we have the 1 minus xi square into omega n. So for any underdamped oscillation, solution is x of t a sine a e to the power minus psi omega n t sine omega dt plus psi. So for the undamped free vibration, so the here piston mass is 2 kg. So we have all the values: undamped natural frequency, damped natural frequency. So we have the damping ratio. So damping ratio we can calculate 1 minus under root of 1 minus omega d by omega n. So we have omega d, omega n. We have omega d is equal to omega n under root of 1 minus xi square. So 1 xi square. So from this we can get the psi is equal to 1 under root of 1 minus omega d by omega n bracket square is equal to under root of omega d by omega. So this is the ratio, so we can directly put it in cpm. So we will get the psi is equal to 0.28. So we have the for damping ratio we have c psi is equal to c by cc. So cc is equal to root km. So from this we can get the c. So c is equal to 2 xi root km is equal to m omega n. So we can say we have all the values of 2 xi m and omega n. So from that we can calculate damping constant. So damping constant is 14.66 Newton second per meter. Now the second question of homework 2 is that a 0.25 meter mercury in a glass thermometer which has a mass of 28 gram in air is suspended by the rubber band and is fully immersed in a cylinder beaker filled with a light oil. When displaced, it oscillates at a frequency of 1 Hz and the motion is damaged from amplitude of 40 millimeter to 10 millimeter in the 2 cycles. So we have to determine the logarithmic decrement, damping ratio psi, and viscosity mu of the oil. So here hint is already given that we have the Newton's equation for the viscous motion and for the linear velocity gradient. So first we have to determine the damping ratio for the observed. So the damping ratio we can calculate from the decay of damp free vibration. So given that the amplitude decays from 40 mm to 10 mm, okay, in 2 cycles. So with 1 hertz damped natural frequency, so that means we have x0, amplitude at x0 is 40 mm and amplitude at x2 is equal to 10 mm. So we know the for the amplitude ratio, x0 by x1 is equal to x1 by x2 is equal to x2 by x3. So for the 2 cycles we can write it down at x0 by x2 is equal to x0 by x1 into x1 by x2. So all are equal, so x0 by x1 bracket square. So we have x0 by x2 is 4, so we can write it down x0 by x1 is equal to 2. So the logarithmic decrement we have delta is equal to ln of x0 by x1, ln of 2 is equal to 0.693. So this is the first thing that we have to calculate, the logarithmic decrement, which is 0.693. And now for the next thing, the damping ratio. For the damping ratio from the logarithm decrement we can directly calculate. So xi is equal to under root of delta square divided by 4 pi square delta square. So we have the value of delta at logarithmic decrement. We can put it here. So we can calculate the psi is equal to 0.1096. So also we can calculate the C, if because the C is required for the calculating the viscosity. So the damping constant is mu A by H. So mu is viscosity of the oil. So damping constant can be determined from the damping ratio. So xi is equal to C by Cc. So Cc is 2m omega n. So we can put it here. So C is equal to xi Cc is equal to xi 2m omega n. So we have omega n is equal to omega d by root of 1 minus psi square. So we can put these values here. Now from the hint, that is the Newton's equation of equation for the viscous motion, we have F is equal to mu del u by del y into A. So which is equal to mu A by H into nu. So to calculate the viscosity, damping constant, we have already know that mu A by H. A is the immersed area, H is the gap between the moving piston and the cylinder. H is the gap between. So the viscosity we can write it from here is mu is equal to CH by A. So calculating the mu, we have to calculate the C. So for the C, we have already value. C is calculated from here. So we will put this C value in this equation, so that we can calculate the viscosity. So we will put that viscosity in the viscosity equation, value of C. So we have all the values of mass is 28 grams, xi is 0.1096, omega d 2 pi, and H is 5 mm gap between the thermometer and the beaker, and A is immersed area, which can be calculated as pi dl. So this is a thermometer, so the diameter is d, so area is pi dl, length of the thermometer. So the diameter is 10 mm and length is 250 mm. So all the values we can substitute here in this equation. So we will get the viscosity of oil is 24.8 Pascal. So the third question of the homework 2 is that a slab door 2 meter high, 0.75 meter wide, 40 thick, and the mass of 36 kg is fitted with the automatic doors closer. The door open against the torsion spring with a modulus of 10 Newton meter per radian. Determine the necessary damping to critically dampen the return swing of the door. If the door is opened at 90-degree angle and the release, how long it will take until the door is within 1 degree of closing. So to solve this problem, we can consider that door can be modeled as a rigid lever swinging about the hinge O. So the door is the rigid lever swinging about the hinge O, and the door has a mass of 36 kg and the width of 0.75 meter wide. It is also given that we have to also given that the door is opened at 90-degree angle and released. So how it so we have to find out how long it will take until the door is within 1 degree of closing. 1 degree of closing. So first let's find out the first equation of motion for this system, for this rigid lever, for this model. Equation of motion is j theta double dot, as the angular equation will be j o about o theta double dot is equal to moment summation. So here is damper will be there. So minus c theta double dot minus of k theta, restoring spring restoring moment. Okay, so c theta for the damper counter moment, and k for the k theta is spring restoring moment. So rearranging, we will get the j0 c theta dot plus k theta is equal to 0. So c theta is the rotational damping constant and k theta is rotational stiffness. So let's calculate the moment of inertia. So j theta is equal to ml square by 12 because the rod rotating about at its end. So ml square. So we have the m is 36 kg and l is 0.75 meter. So the 6.75 kg meter square. So we have the equation of motion as we had derived already. If the let's consider the if the door is critically damped, there will be no oscillation for the door closing. Then there will be no oscillation for the door closing. So the critical damping is can be calculated. It's the critical damping constant is totally dependent upon the rotational stiffness constant and the moment of inertia. So the c theta is equal to 2 root j0 k theta. So this is the rotational damping constant c theta. So we have already have the j naught and k theta. So we will get the c theta is equal to 16.43 for the undamped. For the undamped natural frequency, omega n is equal to root of k theta by j0. So we will get the natural frequency also. Now if you put all the values in the equation of motion with the critical damping, so the solution of the vibration, this vibration will be the theta t is equal to e to the power minus omega n t c1 plus c2t. So c1 and c2 are constants that we have to find out from the boundary conditions. So the initial conditions, from the initial conditions, so initial conditions are given at t is equal to 0 initially. Theta is equal to 90 degree and t is equal to 0, and theta at t is equal to 0 is it will be 0 degree. So the constant c1 and c2 can be calculated at this so the initial at this initial condition. So we will get the c1 is equal to 90 degree and and we will put c1 here, c1 here. So if we take differentiate with respect to time, we will get the velocity. So theta t dot is equal to minus of omega n e to the power minus omega n t c1 plus c2t plus e to the power minus omega n t c2. But we already know the value of c1, so we can put it directly here and solve. We will get the theta t dot velocity is equal to minus omega n theta t plus e to the power minus omega n t c2. So the initial speed at t is equal to 0 is 0, so we will get the c2. From that we will get the c2. So c2 value is 109.54 degree per second. So the substituting this c2 value in the vibration response, so we will get theta t is equal to, we have all both c1 and c2, so we will get the theta t is equal to e to the power minus 1.217 t, that is omega n in bracket 90 plus 109.54 t, c1 and c2. So we have to find out what is the door closing time from 90 degree to 1 degree. So to solve that one, we have the 1 degree theta at 1 degree. So let's solve by guess. So solving this one, we have to guess and iterate numerically, so that what is the time for the for theta is equal to 1 degree. So let's put theta is equal to 1 degree, and we have to iterate for the time t. So first, so this is exponential, so the guess that is exponential function can be written as 1 by 90 by solving this one is equal to 1 by 90 is equal to e to the power minus 1.217 t. So for this iteration we can get the t is equal to 3.697 seconds. But the actual angle is but at this time the actual angle becomes 5.51 degree, which is not, because we want 1 degree because we want 1 degree angle. So for after few iteration we can calculate that at t is equal to 5.355 seconds we will get the theta is equal to 1 degree. So the time taking to close the door from 90 degree to 1 degree is 5.355 seconds. So the fourth question of the homework 2 is a linkage with a length b is pivoted at one end and other end is supported by the spring constant k. A lumped mass is located on the linkage at the position A, at which the dashpot with a damping constant c is also located. Assume that the linkage has negligible mass as compared to the lumped mass m. Write down the differential equation of the motion of the system. Determine the natural frequency of the damped wave oscillation and the critical damping constant cc. So this problem we can solve by directly considering the equation of motion and solving for the equation of motion and solving the parameters. We can get the for this system for solving the parameters we can get the value of natural frequency of the damped oscillation and the critical damping cc constant. But let's go by the step by step for this problem. Free body force, let's do the free body force analysis step by step. Firstly we have to identify the equilibrium position. So the system's equilibrium position was told to be horizontal. Then the spring has extended statically to the counterweight. Now the second step is static equilibrium. Static angular rotation psi is defined from unloaded position to the equilibrium one. Due to mass m, so the damping force is 0 at the static equilibrium because of d psi by dt is equal to 0. So we can directly write down the static equilibrium equilibrium is equal to mga minus mga, this mass mg into a minus of kb is spring force into theta of b. So is equal to 0. So this is the static equilibrium. Now we are going to define the dynamic motion. For the dynamic motion the system up to the equilibrium position, the dynamic coordinate defined from the equilibrium to the perpetuated position. For this we can get the different forces. So now we have to identify the forces, because we have already defined the dynamic motion. Now we have to identify the forces. So when mg acts on the mass, spring force of spring force, this because of this spring opposes the total spring extension, and the dynamic force cb damping force cb opposes the velocity. Okay, so now calculate the moment. We have to calculate the moment. So we have already identified the forces, so now we have to calculate the moment. So to calculate the moment, force times the moment arm length, which is the perpendicular to the force, is the moment. So for the mass, it is acting at an angle of at a distance of a. For the damper force, it is acting at a distance of a, and for the spring restoring force is acting at a distance of b. So now applying the Newton's second law, J naught about point O, J naught theta double dot is equal to moment about point O. So moment of inertia into angular acceleration, ma square theta double dot, is equal to damper counter moment plus spring restoring moment. So damper counter moment is minus of ca theta dot into a, this spring damping force, into a, minus of this spring restoring moment. So spring restoring moment is spring force into the distance, moment arm length b. So we will get the now we have the equation of motion. So the moment of inertia, so we don't know what is the moment of inertia. We have taken the moment of inertia is ma square. So it is like a for the lumped mass system of mass m, it is rotated about point O. The mass m is rotating about point O. So the moment of inertia will be Jo is equal to ma square at a distance of a. So it will be a ma square, and we have the equation of motion. So by rearranging this equation of motion, we have all the coefficients in the ordinary differential equation, ma square, ca square, and kb square. So j is equal to ma square coefficient, c theta is equal to ca square, and k theta is equal to kb square. Okay, so now what are the response of this parameter? So the natural frequency is omega n is equal to k0 under root of j. So we have k theta is kb square, and j is equal to ma square. So we will get natural frequency. Now the critical damping is c theta critical is 2 under root of k theta j. So we can directly write it as 2j omega n. Damping ratio is c theta by c theta critical. So if you put it, we will get ca divided by 2b under root of km. So the damped natural frequency is omega d is equal to omega n under root of 1 minus I square b divided by root of, we have omega n, we already know the omega n is equal to b divided by root k by m. So we can directly write it as b by a under root of k by m 1 minus xi is what, ca divided by 2b root km. So we can directly write it as, so this is the damped natural frequency. Fifth question of the homework 2 is for the given single degree of freedom mass spring mass system of a mass 1 kg and stiffness K is equal to 9 Newton per meter. The damping constant is 1 Newton second per meter. Obtain the free vibration response if the system is released from the distance of 13 mm of the equilibrium position with a zero velocity. So we have to find out the vibration response. What is the vibration response for this system if the system is released from the distance of 30 mm of the equilibrium position? So here we already have the x0. We have x0 is equal to 30 mm. X0 at t is equal to 0. We have x is equal to 30 mm. C is equal to 1 Newton second per meter, which is under damped. So we can calculate the parameters first, and then we can get the response for this system. So the parameters are critical damping for of the system is 2 root km. We have all the values k and m, so we can get the critical damping ratio. We can calculate from C by C critical, so which is from which we can say that it is under damped. As the damping ratio is less than 1, the system is under damped. So the response of the under damped system we have is x of t is equal to e to the power minus xi omega n t x sin omega dt plus psi, of which omega n is equal to, we have already know the root k by m, and omega d is equal to omega n under root of 1 minus xi square. So you will get omega n is equal to 3 radian per second, and omega d is equal to 2.95 radian per second. So for the amplitude x and the phase psi using phase phi using the initial condition at x is at t is equal to 0, x0 is equal to 30 mm, and initial velocity is 0, x0 dot. So the initial displacement, so we can put it this initial condition in the response. X0 is equal to x0 is equal to e to the power minus 0 x sin 0 plus 5. So we will get equation 1. Now from velocity, first we have to calculate the x dot of t. So xi minus of xi omega n e to the power minus xi omega n t x sin omega dt plus 5 plus, as we have differentiated, so omega d e to the power minus xi omega n t x cos omega dt 5. Rearranging, we will get this one. So the initial velocity at t is equal to 0. Initial velocity is we can put it in this equation. So we will get x cos psi is equal to xi omega n by omega d x of 0. Now equation 1 and 2. From equation 1 and 2 we can divide equation 1 by 2, which gives phi is equal to tan inverse of 30 mm 30 by x cos phi x sin phi by x cos phi divided by psi omega n omega d. So if you put this one, so we will get phi is equal to tan inverse of phase angle. We will get phi is equal to tan inverse of under root of 1 minus xi square by xi. So we have already value of xi is equal to 0.167. So we can, if you put it here, we will get phi is equal to 80.41. So now if we put this in the equation number 1, value of psi, so we will get the x is equal to 30.43 mm. So if we put capital X amplitude and phase angle in the equation, this response we will get. So x of t is equal to e to the power minus 0.5 t, 30.43 sine, 2.95 t plus 1.40 reading. This is the response for the given system.